I'm using this to help with the quiz question about heat and phase changes. Okay, here we have something called latent heat. The word latent means that there's no real change involved. So when I say latent heat, we're talking about heat that really isn't changing the temperature. It's just changing the actual heat energy. So we have this thing called a phase change diagram. And here you'll notice that we have all three phases, solid, liquid, and gas. And we can either go up or we can go down. So I'm going to start with the solid and I'm going to work my way up. Here, we know that's solid. Let's talk about it in terms of water, because I think that water is like the most, thing that we know the easiest. So over here, let's think of this as ice, liquid water, and water vapor. Ice is obviously the coldest. Therefore, we expect it to be the lowest in temperature and, of course, the lowest in heat energy. Now, let's say we take that piece of ice and we put it in a pan on the stove and we start to heat it up. Well, of course, it's going to start to increase in temperature. And as it goes up in temperature, it's also going to be going up in heat. So we're rising on the y-axis and we're also rising on the x-axis. We have a positive slope. However, at a certain point, this is going to start to melt. This part of the phase diagram is the melting phase. And notice, we no longer have a positive slope. We actually have now a zero slope. It's a horizontal line. So we have zero change in temperature. However, we are continuously increasing in heat. When that happens, when heat is increasing, but temperature is not, we call that latent heat. And in this case, latent heat has a special name. So whenever we're melting, we call that the heat of fusion. Now, way back when we learned about nuclear chemistry, we learned that fusion is when two things combine into one, or more than two things combine into one. So you're probably asking yourself, if we're melting, we're not combining, we're actually separating. See, here the particles are really compact and condensed, they're really close. And as we melt, they get further apart. So why are we calling it heat of fusion? That makes no sense. But what happens is that the amount of energy that was absorbed to melt is the exact same amount of energy that would have had to been released to freeze. Therefore, whether we're melting or we're freezing, it's the same energy. So when they came up with the name heat of fusion, they were actually considering it going in the opposite direction. They were considering liquid freezing to water. So these particles coming closer together and fusing into this solid form. So that's why we call it heat of fusion. So it can be either melting or freezing, same number, it's just going to have an opposite sign. If we're melting, we're absorbing, therefore it's going to be a positive heat. And if we're freezing, then we're releasing that heat, therefore it would be a negative heat of fusion. So again, all dependent on the sign. All right, as we continue up our ladder, now we're in the liquid form. We're eventually going to get so hot that that liquid water, because remember, it's still in the pan, we're still heating it up on the stove, is going to start to boil. It's going to start to bubble. And eventually, we're going to get water vapor. So we're going to start to evaporate. From here, we also have a special name for this vaporization. Notice, again, heat energy is increasing, however, temperature is not. So yes, this is latent heat, but we also call it heat of vaporization. And that makes a lot of sense, right? It's the amount of heat that's needed to vaporize. But of course, if we were going in the opposite direction, we're not going to call it heat of condensation. We still call it heat of vaporization, even though we're actually condensing. Because again, that's the same value, it's just the opposite sign. Okay, so heat of vaporization would be absorbed, therefore it should be positive. Whereas if we're going from the gas to liquid, we're releasing heat to go down in temperature, down in heat energy. So therefore releasing this would be a negative heat of vaporization for condensation, positive heat of vaporization for vaporization. All right, last thing I want to mention, when we're talking about the actual phase change, we're talking about this specific part of the diagram. So you notice, when we're in a solid form, we're not changing phase. All of this change in temperature does not involve a phase change. However, the phase change starts here and ends here. There's another phase change. Starts here and ends here. So for these phase changes, for the actual event of the phase change, is there any change in temperature? So I'm hearing you guys in my head, I'm hearing a bunch of people saying no. I know that's probably crazy. I miss you guys, miss actually having class. But yes, so when we have this change, this phase change, there is no change in temperature, okay? That's not to say that you can't involve a phase change with other aspects being, so maybe we had a solid and the solid was super, super cold. Maybe it started off down here and eventually we heated up all the way to a temperature maybe up here. So in your future chemistry careers, you're going to see that you're going to have to take into account multiple parts of this diagram using multiple different types of calculations to figure out total changes. But for now, we're going to keep it simple, and we're going to consider the phase change from this point to this point, no change in temperature. Okay, hope that helps.